Crazy Hat Chemist. So another video on acids, bases, and titrations. Bam! So today we are talking about a titration example number 3, our final titration example. We're going to do a weak acid titrated with a strong base again. But we're going to do more than the 3 basic points. We're going to add on 2 more points here to this graph. Okay, so here is our problem. We've got 50 milliliters of a 0.1 molar acetic acid, that's CH3COOH, solution is titrated with a 0.1 molar sodium hydroxide solution. So there's something that's very interesting about this problem and very common, but you should be able to recognize this. And that is the concentration of both the weak acid, that's acetic acid, and the strong base. The concentration is the same. And being that the concentration is the same, there's something that's very interesting that will pop up here on this problem. So make sure you pay attention to that. And it only applies when the concentrations are exactly the same. So here we go. What is the pH before the titration begins? This is like an ice table. We have done this before. This is the first calculation that we always do. Calculation number 2. What is the pH at the halfway or the midway point? This is the same calculation that we've been doing before as well, with the halfway or the midway point calculation as well. Okay, number 3. What is the pH at the equivalence point or the end point? Again, that's our third calculation. We've been doing that one as well. Okay, not a problem. We should be familiar with these 3 different calculations. Now, we're going to add another one. What is the pH with the addition of 45.0 milliliters of the base? Okay, now we haven't done that yet. Okay, and then the 5th calculation, what is the pH with the addition of 52.0 milliliters of base? Makes you wonder. Okay, so the acid dissociation constant, that is the Ka for acetic acid, is 1.8 times 10 to the negative 5. That times 10 to the negative 5 lets you know that acetic acid is a weak acid. It's not a strong acid because the Ka is less than 1. Okay, we're going to make predictions as to what you would expect the pHs to be. So before titration begins, what do you think the pH would be? You have acetic acid in there. You have not used any sodium hydroxide. Well, the pH better be less than 7. At the halfway or the midway point, now we are talking about that buffer region. So what would the pH be? Is it 7? No, of course not. It is certainly less than 7. And at the end point, where would you think that pH would be? Now remember, it's a weak acid titrated with a strong base. And at the equivalence point or the end point, that's when the moles of the acid, acetic acid, is equal or equivalent to the moles of the base, the sodium hydroxide. And at the equivalence point, then the strong always wins. That's just like in life. Unfortunately or fortunately, the strong always win. And therefore, the pH is going to be greater than 7 at the equivalence or the end point. Okay, now, what is the pH going to be at the 45 mils and the 52 mils with the addition of that sodium hydroxide base? Well, to answer this question, you really need to draw a titration graph. And based on the 3 previous calculations, that is what's the pH before titration, what's the pH at the midway, halfway point, and what's the pH at the equivalence or the end point, then you will be able to figure out where the volume of base that you have added and what those pH values are. And then based on that graphic, you will be able to make a prediction at both 45 and 52 milliliters. Okay, so this is our graphic here. It is a weak acid titrated with a strong base. Notice that the pH is on the y-axis, the strong base is on the x-axis in volume. Notice that this pH initially starts at a low pH and then it moves on up. Okay, so before titration, that's an ice table with just the acetic acid. Okay, at the halfway or the midway point, we're right in the middle of that buffer region of the acetic acid and its acetate ion concentration of the conjugate pairs are equivalent. And at the equivalence point is when the moles of the acid equal the moles of the base that's required. And that is the equivalence point or the end point of that titration. From these values here of the pHs and of the milliliters of sodium hydroxide, then I'm going to be able to answer that 45 mils and the 52 mils respectively. All right, so let's get moving on this here. So before the titration begins calculation, we're going to use an ice table to determine the pH, which is based solely on the acetic acid, since sodium hydroxide has not yet been added at this point in time. Okay, so we have acetic acid, that's an acid, that's CH3COOH, plus water. Water is a liquid. Now, in order to write the products, we're going to write the conjugate pairs to acetic acid and water respectively. Since it's an acid, that's acetic acid is an acid, we're going to produce hydronium ion. So the conjugate to water is the hydronium ion. That's an addition of a hydrogen. Where did that hydrogen come from? That came from CH3COOH, that last H. So I'm going to remove that last H on the acetate ion, okay, and I will get the acetate ion. So I have acetate ion and the hydronium ion. Notice the reactant side has a net charge of 0. The product side has a net charge of 0. What's important is that the net charge on both reactant and product side is equivalent. Okay, now we're going to do an ice table. That's ice right there, ICE. That's initial change equilibrium. We know the initial concentration of this acetic acid. That is 0.100 molar. Nothing for the water. And of course, on the product side, nothing and nothing. Those are both zeros. Now this shift in equilibrium, the shift occurs such that it shifts towards products. That means I'm going to decrease the reactants and increase the products. I'm going to look at the stoichiometric coefficients, which is 1s across the board with all the reactants and products. So it's going to be a minus 1x, nothing for the water again, plus 1x and a plus 1x for both of the products. I'm going to add up my initial and my change to get my equilibrium on my data table. That's for the acetic acid is 0.100 minus x, nothing for the water again, and x for the acetate ion and x for the hydronium ion. I need to write the Ka expression for this. Just like any equilibrium constant expression, this is the acid dissociation constant, the Ka. It's products over reactants with the stoichiometric coefficients as exponents. So the Ka is the acetate ion times the hydronium ion divided by the acetic acid. Water is not included because that's a liquid, of course. Now I'm going to plug in these values at equilibrium right in that Ka expression and using the Ka that was given to me at the very beginning of this problem. So the Ka is 1.8 times 10 to the negative 5. The acetate and hydronium ions are both x respectively, and I'm going to multiply them together, so that's x squared in the numerator. My denominator is 0.100 minus x. Now, do I use the quadratic or not? That's the question. So, if 100 times the K is less than the initial concentration, I can use the approximation and I don't have to use the quadratic. So, 1.8 times 10 to the negative 5 times 100, is that less than 0.1? And yes, it most certainly is, so I'm going to get rid of that minus x in the denominator. Now I'm going to solve for x. So solving for x, I'm going to take 1.8 times 10 to the negative 5, multiply that by 0.1, and then take the square root of that, and that will equal this value of x. X is equal to 1.3 times 10 to the negative 3. Now I'm going to look at my ice table and figure out what does x equal. X equals the acetate ion concentration, okay, which is 1.3 times 10 to the negative 3 molar. X also equals the hydronium ion concentration. The hydronium ion concentration is 1.3 times 10 to the negative 3 molar. Now I am solving for the pH on this problem, and so I'm going to take the negative log of this value here. I'm going to take pH is equal to the negative log of the hydronium ion concentration, and then I'm going to get a pH of 2.89. Notice it has 2 decimal places. So I'm going to ask myself, does this pH of 2.89 make sense? Did this correspond to the basic graph of which I drew initially at this problem? Well, of course it certainly does. It does because you predicted it would be acidic, because there is no base that is added at this point in time, because it is just acetic acid and only acetic acid, so it should be a pH that is less than 7. Okay? I am the crazy hat chemist, so of course I gotta wear a crazy hat, and I'm wearing the iconic hat here, of course. Okay? Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Get a sticker. You need one of these. See you later for next time. Look for part B on this problem. Bye for now.